back on stage for the Q&A session. So we'll be now talking about machine learning, artificial intelligence in avionics system.
Hi, everyone. Okay, so this is the talk. I'm trying to keep it as concise and interesting as possible, and we can talk in detail later at the panel session if you have more questions. The outline of my presentation is going to be in this order. To start with, I would like to introduce me and my company mainly to the audience because we are not very well known in the industry. We are basically a startup. We're about 6 years old startup now called Daedalean AG. We are placed in Zurich, Switzerland, and we are by now about 100 people with a good mix of workforce between the academia, researchers, aerospace specialists, certification specialists, pilots, and so on. Our mission is to provide certified safety-critical artificial intelligence systems to co-pilot and pilot the aircraft of today and tomorrow. When I say the aircraft, I include the eVTOLs as well of the future. When the company was started in 2016, our aim has been to build the world's first fully autonomous AI solution to outperform a human pilot in the cockpit. And to that effect, we took, for example, a CPL Edge training handbook to break down into different factors of what's required in piloting. And that was the basis for us to get into this journey of building systems over a period of time. Just to show a scenario of how in the future, when we have in a semi-urban or an urban environment, how the flight, a typical flight looks like for a helicopter or an air taxi. You take off from a heliport, you need to go to your destination. On the way, you need to avoid the power lines. Yesterday, David Sola was talking about power line detection. That comes to mind. You need to avoid other airborne objects, which could be other airplanes, other taxis. You need to maneuver to your destination, making sure you don't get into non-VMC conditions, avoid the clouds, avoid terrains, and basically finally go and land where it was planned, at a planned heliport or a vertiport, or even in emergency situations, find a place to land where there is no marked place to land. So this you can map also to an urban environment and replace most of these with buildings of different sizes. So with that in the background, today we have three systems or three products that we have ready. We haven't certified them yet. I'll come to that later. But basically, we are trying to provide answers to the three main questions. Where am I? Where can I fly? And where can I land? So where am I? It's basically positioning of the airplane that you're flying, of the whatever airborne object you're flying, using machine learning solutions with the cameras taking the video of the landscape below you. So we have systems that can provide continuous outputs of position, heading, the velocities, and height above target, and so on. So even if there is no GPS, we can provide this information. That is the main goal of this whole thing. Then where can I land? So we have the visual landing guidance system, which has been tested several times. And this is basically a system purely based on cameras and machine learning software, making sense out of it. And not only looking for an airstrip to land on, but also providing accurate guidance for the aircraft to land, even if there is no ILS system there. Then, of course, where can I fly? There's the detect and avoid, or for now, let's call it the visual traffic detect function, using the cameras, looking looking out of the airplane to find if there are some other aircraft, other airborne objects, and then making sense out of if that's an airplane, that's a helicopter, if that's a drone, balloon, and whatnot. Categorize the different kinds of airborne objects, and then provide the time to collision if you're on course to that. So this works even if there is no ADS-B on the other aircraft or on your aircraft. So these are the solutions we have working today, and these are solutions we want to certify in the future. Just a bit of additional information. These systems are already being tried and tested on potential customer aircraft with the data we provide to them in terms of the documentation and design data and so on, and they are in operation in a trial phase. Now, coming to the core of my presentation, what I really mean by fitness for purpose and absence of unintended function. So I think most of you in the audience are aware of this aircraft systems certification issues, or the certification paragraphs that we mainly have to show compliance to, namely the 1301 and 1309. It will be 2500 and 2510 in the new amendment of 23, and hopefully also for the other class of cert standards. Basically, these are not the exact text of these paragraphs, but I'm paraphrasing to break it down to what I want to show. Basically, we want to show that the equipment must deliver its intended function, no more and no less. Basically, it shouldn't deliver any unintended function. That's the main part we need to do. And it has to provide this function under its installed environment under all foreseeable conditions, which means both in abnormal and normal conditions. So how do we do that? Unfortunately, I had sent an updated presentation, which is not updated here, but it's okay. Before going to how we do that, I want to quickly take a minute to talk about machine learning. Why do we want machine learning in any kind of applications? The main reason we want to use machine learning is in any perception-based function, machine learning is the only possible way to provide superhuman performance, just because of the fact that you can have several cameras looking at all different areas around the aircraft and keep making sense out of it. Because we humans have a limited vision, limited concentration time, and we want to use this machine learning to support the human by providing these functions. So a quick overview of how a typical camera-based machine learning function works in our architecture is there is a camera or more cameras fixed outside the aircraft, looking out at the outside world at a certain high-resolution picture quality and high frame rate, and each of these images are sent to a computer, which is the main computer which makes sense out of this whole thing. So initially, we just break down the main image into smaller blocks of the images, and then those images are sent to the neural network. Here, in this case, it uses a convolution neural network, which basically has a simple function. It has to say, is there an aircraft, yes or no? Is there any object, yes or no? Is there a runway, yes or no? That's all it does. And then it sends the information back to the traditional software, which basically starts tracking this target and calculating the time to collision or guidance in terms of azimuth and elevation to land, for example. So in the whole chain, it's only the recognition or answering the question if there is an object of interest, yes or no. That's what the neural network is doing. Now, coming back to the certification challenges, which I started earlier. Traditionally, today, I think most of you are aware of this, so I'll not go too much in detail, but just a couple of words about the system development process. You start with the preliminary architecture, you break them down into functions, you follow the SAE ARP 4754A to develop the process, develop the design, and then you also do the safety analysis using the guidelines in ARP 4761. It is kind of an iterative process where you continuously improve the design to meet the safety objectives set forth in the safety standards. And then each of these functions are broken down into systems of systems, different items, and when it comes to hardware and software, you follow the DO254 or DO178 respectively. Now, this design assurance process is not in itself providing any compliance to any certification paragraph, but basically it is providing the confidence that enough rigor has been applied during the whole development and testing process that you have been able to remove the sources of error as much as possible. Now, where does AI sit in here? So what's important to know is in the whole process, the top level is based on the functions, the internet functions that is defined at the start of the process. So it talks about the intended function. It doesn't talk about how it is implemented. So depending on how it is implemented is the way we have to go to show this assurance. So for the software and the hardware, we have the DO178 and DO254. What do we do for the items, which the neural network or machine learning items? So that is the core of the matter that we need to find out, or we need to prove that we can show the fitness for purpose. And also, the traditional design assurance doesn't suffice for a machine learning process because in a machine learning development, the focus moves from requirements to data mainly. So it is a lot of the requirement traceability has to pass through the data. When I say the data, we are talking about the data that is used for training the neural networks, the data that is used for validating these requirements, and of course verifying at the end on the system level. So, which includes how we select the data, how we process the data, how we manage, etc. My face is like this because I had sent an updated presentation and it was not updated. But anyway, I'll come back to this slide. Before that, I want to say that in order to find how we want to show or define a process, we are very lucky that EASA has been extremely active, and they have been the torchbearers when it comes to artificial intelligence and how to come up with processes to show the assurance. And since 2020 or 19, EASA started an IPC, Innovation Partnership Concept. Sorry, I don't know what I've forgotten right now. It escapes my mind. So we worked with EASA to develop together a concept for design assurance system. We first partnered in 2020, where we did a small project on landing guidance, where we came from a research perspective. EASA came with the safety and regulations perspective, and we published this CODAN 2020 together, which is available publicly. And also, we had a follow-up project in 2021 where we again published an updated one where we did a second project using the learnings we did, and eventually, and we kind of came up with this so-called W-shaped model, which I'll come to later. And as a side note, FAA was also interested in what we did and how it fits into their policies. And last year, we also did a project with FAA for the landing guidance system, and the paper is also presented on the FAA website. These are all like very well researched, and they look like PhD theses. And if someone is interested, I can provide the links later, and that can be read. And also, just talking about the EASA AI roadmap, based on all these different projects we did together, and also EASA's initiative, end of last year, a concept paper for first usable guidance has been published, which is what we are trying to follow in an ongoing project. And that's, at the moment, it's issued for level 1 AI/ML systems, which is basically pilot assistance. A level 2 guidance is expected to be published, I think, end of this year or so, where it will be an update to move on to a more augmented system with machine learning. Now I'll come back quickly to this slide. So I think most of you know about the V-shaped model in the development, as in the top of the right, on the right top of the screen. So you write down the requirements in detail, you break them into systems and subsystems, and you perform the implementation, and then you verify at each level. That's the general V model. What has changed now, or for the items which are driven by machine learning, is basically a bit of adaptation of this V model, but introducing a bit more focus on the learning and implementation of the modules, which gives this kind of a kink at the bottom. That's why we call it the W-shaped model. So until the requirements are defined, it's the same. But then when it comes to the next step, for the software and hardware parts, follow the usual V-shaped model. But for the machine learning parts, we get into this process where we need to show how we manage the data, the independence of data, how we gather the data. When I say data, it's about the training and validation and verification. And we have to make sure that the data represents the data distribution is according to the outside world, and there is no bias in the data, and so on. And then how we manage the processes, learning process, like how we define the algorithm which does this learning, and so on. How we select the algorithm, and then how we train the model. And then we have to show, verify that the learning process has been properly followed. And then we implement the models on the target hardware. We verify it at the box level, and then eventually on the inference model, which is basically the target hardware. We also want to show that there is it is showing what it is. We have to verify that the performance is as expected, and eventually we need to also have an independence in the independent data verification of the learning process. And then it goes to the usual V-shape as it was before. I will not go into each of these boxes in detail because that doesn't fit into the 25 minutes that we have today, but we can talk about it later. What I want to talk about specifically is how the independence of data that we must follow for the training set, for the validation set, and the verification set, because that's the holy grail of this whole system. We need to make sure that the data that is trained, that's used for training on the model, is completely independently selected from the validation data that is used later on. There is also this issues of underfitting or overfitting of the samples. We need to be very, very careful in gathering the data and making sure that we have the data for distribution as in the outside world, and then we need to have the same kind of distribution also in the other sets of data. So this is the learning assurance part, which is for the neural networks, which is in synchronization with the design assurance for the general software and hardware aspects. We talked about this. So a project using machine learning for detect and avoid is ongoing right now. We call it the pilot eye. We are doing it with Avionics, the American avionics provider, and we have applied for an STC. A CRE and an IP have been issued and closed, so we should hopefully have a certified ML application sometime next year. I want to talk about the roadmap a bit, I think, but I've been told that I'm running out of time. But as a company, we have a vision to develop these systems in general in the same phases like in the AI roadmap, initially starting with pilot assistance, then advanced assistance, and eventually monitored autonomy. And we also want to work on the secure V2V broadcast communication to make sure in an urban environment, when there are too many, in a city like London or Singapore, when air taxis are flying, there is no way an ATC can regulate the traffic. There has to be some way of self-organized communication between the vehicles to make sure there is sufficient space and separation between them. And coincidentally, NASA came up with a white paper, I think last month or 2 months ago, calling it the DFR, Digital Flight Rules to complement the IFR and VFR, where again the stress is on cooperative practices, including shared traffic awareness and vehicle-to-vehicle communications, and making the self-separation automatic. So we are just happy that we are looking at things the same way for the future. That's all. That's where I end the talk. Thank you.